Hello, welcome to this video. This is 8-4 and today we're going to graph exponential functions with a new base, a new irrational number that I'm going to go ahead and introduce to you. The first thing I want to talk to you is about factorial. Now n, and it looks like an exclamation point, factorial is read as n factorial, where n can be any whole number. Now, n factorial is equal to the product of all of the whole numbers from n all the way down to 1. So 0 factorial is defined as 1. 1 factorial is equal to 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which gives us 6. 4 factorial, now that would be 4 times 3 times 2 times 1, which gives us 24. And 5 factorial would be 5 times 4 times 3 times 2 times 1. So another way to write that would be 5 times 4 factorial, which gives us 120. Okay. So, in math, you learned about sequences. Now, sequences of numbers are just any numbers that have a set pattern, right? 2, 4, 6, 8. It could be geometric. 2, 4, 6, 8, where we're adding 2. Or it could be geometric where we were multiplying by 2. 2, 4, 8, 16. Now, a series, which is a new term, a series is when the terms of a sequence are added together. And one famous series is called the Maclaurin series. And here is an example of the Maclaurin series. And you'll see this Greek letter, which is called sigma. And it just means you're adding up. It's the summation of all of the terms from k equals 0, so I would plug in 0 into my function here, and I would go all the way to infinity. So I'm not going to stop. I'm just going to keep getting bigger and bigger and bigger. Well, an example of this, what this is equal to, if I plugged in 0, we have 1 over 0 factorial. Well, that's 1 divided by 1. That gives us 1. 1 over 1 factorial. Well, that's 1 divided by 1. Again, that's 1. 1 over 2 factorial. That's 1 divided by 2. So that's 1/2. Plus 1 over 3 factorial, plus 1 over 4 factorial, 1 over 5 factorial, so on and so on and so on and so on and so forth. We are just adding all of these terms together. Now what you should notice about these terms is that they are getting smaller. 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1/20 plus 1 over 720, so on and so forth. They're getting smaller and smaller and smaller. Now, it's interesting what this number approaches, and it approaches a finite number because these numbers get smaller and smaller and smaller. If you want to go ahead and you want to use a calculator to add these numbers up in the series, you can find out what this value is. I'll allow you to pause me now, but I'm going to go ahead and show you what this number is. So the number that you should get approaches somewhere around 2.7182539, so on and so forth. Now, as we add more and more terms to this series, the sum approaches an irrational number, which we call e. Now, e, which is used just as a symbol to represent this number, similar to how pi is approximately 3.14, e stands for Euler. So, a famous mathematician named Euler discovered this number, and it is often called the natural base. It's used extensively in scientific and other applications, especially in exponential growth and decay. So e is approximately 2.718. I would hope that you would remember at least that information, but if we go on further, we have 2812828. Okay? So that is the number e, and that's our objective today. We want to go ahead and graph exponential functions with base e and identify the key features. So, identifying the base e functions as growth or decay. Well, here is the structure, again, for an exponential function. F of x equals a times e to the power of x minus h plus k. That would be exponential growth, where our coefficient of our exponents are positive. And notice that makes sense because e, approximately 2.7, that's bigger than 1. So that's going to be exponential growth. Exponential decay when we have a negative coefficient. So you'll see e to the power of negative x plus h, or in factored form would be a times e to the power of negative x minus h plus k. All right, we are going to go ahead and graph the horizontal asymptote, which again is going to be our k value, and we're going to have to plot the key points, hopefully including a y-intercept and a 0, as well as the end behavior. So let's go ahead really quickly. We're going to look at these three functions, and we're going to identify the function as exponential growth or exponential decay. Well, our base is e. Our base is e, which is approximately 2.718. Well, that's greater than 1. That means that this is exponential growth. Our function is going to grow there. Example number 2. Here, again, our base is e. That is exponential growth. And then lastly, for h of x, here we have e, but it's raised to the power of negative 1, which is 1 over 2.718. This value is less than 1. Less than 1. This is going to be exponential decay. All right, so very straightforward. If you have base e with a positive exponent, it's exponential growth. If it's a negative exponent, exponential decay. All right, so here is your introduction to the base and parent function e to the power of x. You'll notice we have a table of values here. We have, as x is negative 2, the function f of x equals e to the x is 0.135, very small. If I plug in negative 1, that's 1 over e. If we plug in 0, we get 1. Anything to the power of 0 is 1. And if we plug in 1, we get e to the first, which is just 2.718 approximately. If we plug in 2, we get approximately e squared, which is 7.389. When we're graphing today, these are the two key points that I care the most about. That you know that if we plug in 0, we get 1, and if we plug in 1, we get approximately 2.718. Now, the domain for this exponential function is similar to all of our other exponential functions. We go from negative infinity to positive infinity. The range is from 0 to infinity, and that's just dependent upon our asymptote. Since our horizontal asymptote is y equals 0, that's our range. If our asymptote was shifted up 2, then it would be 2 to infinity. The end behavior, as x goes to negative infinity, our function approaches the horizontal asymptote, which in this case is 0. And then as x approaches positive infinity, our y values increase unbounded to positive infinity. So let's go ahead and graph a function here. We're given the function g of x equals 2 times e to the power of x minus 2. Minus 2. Lots of 2's going on here. That's the lucky number 2, I guess. A is 2. Our h value is 2. And our k value is negative 2. So the first thing that you want to get is your horizontal asymptote. That is going to be your k value. And in this case, y equals negative 2. Your second thing that you want to find is our pseudo origin. We want to go ahead and build in our transformations. So our origin is 2, comma, negative 2. That's just h, comma k. So there's our pseudo-origin. Let's go ahead and let's plot this. So I'm going to place my axis down here. Since we're growing, we have a stretch by a factor of 2, and then also 2, we have a horizontal asymptote down 2. Okay, and then our y-axis, since we're going right 2, I'm going to shift mine to the left about 2 units. Okay, so here's our x and our y-axis. Okay, and then I'm going to plot my pseudo-origin, which is 2, -2. So right here, there's my pseudo-origin. Okay, and step 3, I'm going to plot the key points. Key points, which we only have 2. We have 0, which gives us 1, and we have 1, which gives us E. So I'm going to go from my pseudo-origin up 1. I'm going to go right 1, and then up about 2.7. Those are our 2 key points. From there, you can get a rough image of what your function looks like. Oh, actually, these points, let me do this. I forgot, those key points, we need to multiply by our a value. So I have to multiply my y values by a, which is 2. So I'm going to multiply by 2, multiply by 2. So instead of up 1, I'm going to go up 2. And instead of up 2.7, I'm going to go up 5.4. Let me just double check that. 1, 2, 3, 4, 5.4. Okay, good. So it's going to grow very, very steep. Make sure you put arrows on both ends. Okay, and then we're going to go ahead and answer some key features. So this is exponential growth. Exponential growth. Our domain in set notation are the x values where negative infinity is less than x less than infinity. And interval notation would be negative infinity to positive infinity. Range, this is the y values. And in this instance, y is greater than -2. That is often tied again to your horizontal asymptote. We're at -2, and my function's growing, so that's y is greater than -2. And as an interval, that would be -2 to infinity. The horizontal asymptote, y is equal to -2. And then our end behavior, as x goes to negative infinity, the function, which is g of x, approaches -2, our horizontal asymptote. And as x goes to positive infinity, our function is increasing towards positive infinity. Okay, so there's our graph. All right, here is example 2. In this example, we have, what's interesting is our exponent. So notice I have negative x minus 3. So I'm going to go ahead and rewrite this. This is negative e, and I'm going to factor out that negative. I want it in factored form. And that's going to cause me to change my coefficient in front of the 3. Okay, so what we have here, we have an a value that's -1. We have a c value that's -1. We have an h value that is -3. And a k value, which is a +1. So I'm going to go ahead and graph this the same exact manner. Step 1, I need the horizontal asymptote. That depends upon your k values, so y is equal to 1. 2, our pseudo origin, that is h comma k, which in this case is -3, comma 1. And then we'll go ahead and we'll use our key points to give us the rest of the points, the rest of the information on the graph. Okay, so again, 0, 1, 1, e. And we do have a values, which our a value here is -1, so I'm going to multiply all of these by -1. So we get, I'm actually going to go down 1, and then I'm going to go down 2.7. And then we also have a c value. So that's going to affect our x values. So instead of going right, I'm going to go left. Okay. So let's go ahead and graph this. I do have a vertical reflection down, so I'm going to put my axis up here. And then we're shifted left 3, so I'm going to go right 3 on my axis. Okay, and here's y. And we have our horizontal asymptote at a +1. With our pseudo origin on that asymptote left 3. So there's our pseudo origin. Okay, and then I'm going to plot my key points. So 0, -1. I'm going down 1 value. And then -1, so I'm going left 1. And then I'm going to go down 2.7. So 1, 2.7. Okay, and here is our graph. This is exponential decay, because that base is less than 1, right? E to the -1 power. Our domain, -infinity less than x less than infinity. So -infinity to infinity. Our range, these are the y values where y is less than 1. So notice the shape and structure of our graph. All of our y values are below 1. And so that would be -infinity to +1. The horizontal asymptote, y equals 1. In our end behavior, the left side, as x goes to -infinity, our function g of x goes to -infinity. And as x goes to the right side, +infinity, our function's approaching the asymptote, which is at +1. Okay, here is a practice problem. Please go ahead, pause the video. I want you to try this example. Okay, here is a straightforward basic example. We're shifting left 1, down 3. And there you go. There's your graph. Again, the key points that I would expect to see on your graph are these 2 points. Our domain, -infinity to infinity. Range, -3 to +infinity. Horizontal asymptote is -3. Y equals -3. And then our end behavior on the left side, as x goes to -infinity, the function's approaching -3. And as x goes to +infinity, g of x is approaching +infinity. Okay, here is example number 2. Please pause the video and try this example. Okay, and here is the solution. we have a stretch factor of 1/2, and we had a negative c value. So we have that horizontal reflection, and we ended up shifting to the right 4. So again, the key points that you would want are right here, 4 up 1/2, and then left 1 up 1/2 of 2.7. Okay. All right, so really quickly, closure. Using this graph, what is the value of k for the function h of x equals e to the power of x minus 2 plus k? Well, we know that our horizontal asymptote is k, so in this case, since our horizontal asymptote is y equals 4, this implies that k is equal to 4. All right, that's going to do it for this video. In this video, we learned how to graph base e functions, exponential growth and decay base e functions. Go ahead, like and subscribe. I'll see you in the next video.